To introduce the idea of inverse functions, it's helpful to start with something familiar. If our action is to put on socks and then put on shoes, the inverse is how we would undo that to get back where we started. So we would want to, of course, take off shoes and then take off socks. Just in case you've been doing it wrong, this is the method that works. Looking at this, we can see a couple of things. One of them is that the purpose of an inverse is to get back to where you started from. The other is that we can see that we had to invert both actions. Putting on the socks got undone by taking off the socks. Putting on the shoes was undone by taking off the shoes. But not only did we invert both actions, we also reversed the order. So we can now apply this in a mathematical context. If our action is to multiply by 2, then add 3, if we invert each operation and reverse the order, we'll start with the inverse of adding 3, which is subtract 3. And we will then do the inverse of multiplication by 2, which is divide by 2. To illustrate that this works, we could start by just choosing any number. Since this is a video, I can't really ask for a number from the crowd, so I'll just make one up. Let's say that I started with 5, and I'm applying my action. My action says to multiply by 2, and then add 3, which gets me to 13. So this is my starting point and my ending point from the action. I'm now going to start applying my inverse. My inverse tells me to first subtract 3, and that gets me 10, and then divide by 2, which gets me back to that 5 that I started with. So this also helps us to illustrate the goal of an inverse mathematically. If we started with 5, then after applying the function and its inverse, we want to get back to that same 5 that we started from. So the idea is that an inverse should undo an action. The way we're going to define this has to do with functions, of course. So we say that if two functions f and g are inverses of each other, then that means that f composed with g of x is equal to x. So remember that this is composition of functions. That's what that little circle means. And to make sense of this in the context of what we're talking about right now, notice that we started from x, we then applied the function g, we then applied the function f, and we get back what we started with as a result, which is that x. So that's like starting with this 5 up here, applying our action, then applying the inverse to the result, and ending up with 5. The second part of this is just saying that it has to work in both directions. F composed with g of x is x, and g composed with f of x is x for all x in the domains of each. Generally, if one direction is true, the other will be also, provided that they have compatible domains, right? If they both have domain all real numbers, then you're never going to have a problem in one direction that didn't exist in the other direction. So often it's sufficient to check one direction when we're checking to see if two functions are inverses, but the definition does require that both be true. Also, the language we use to refer to an inverse function is this f, what looks like a power, -1. We read this as f inverse, and it is not the same thing as the power -1. Taking a function to the power -1 would basically take its reciprocal In most cases, that's not the same thing as the inverse of the function. So this is new notation, and we have to look at that and just know that that means the inverse function of the function f. So that would be the function g as referenced in this definition. So let's take a look at a function that is defined numerically. Here we have a function f, which is defined by this table of ordered pairs. Now we know that it's generally true that f of x is equal to y if we're in the most generic context. If we're looking at an inverse function, then what we want to do is back it up, right? What we're used to being the case is that x is our input and y is our output. For f inverse, we want y to be the input and then x is the output, at least in the context of the function f. So looking at a table like this, f inverse of 1, we would want to interpret that as giving us a y value and asking us what the x value is that goes with that y value. So looking at this table, we now are looking at y values to identify 1 and reading the table backwards in order to evaluate the inverse function. So we would say that that's equal to -3. So we can see it's true that if f of -3 is equal to 1, then it's also true that f inverse of 1 is equal to -3. This is the function that undoes the function f. Given that that's true, we can see that replacing or swapping our input and output variables is how we read a function or an inverse function from a function that's defined numerically. It also works to define the whole inverse by just swapping the rows. So if we want to find an inverse function given a function, all we need to do is put our y values where x is, so -3, 1, 2, 4, and put our x values where the function output or y would go. So -4, -3, 1, and 2. Now if we're reading f inverse from this function, f inverse of 1 again, because this function represents f inverse, we would read it in the straightforward direction. So we want to keep track of when we would read it backwards and when we would read it forwards. Here we would read it just as if we were reading any old function, because this is the function named f inverse, so this is equal to -3.